Hybrid pooling with wavelets for convolutional neural networks by Daniel Treviño Sanchez and Vicente Alarcón Aquino. The need to detect and classify objects correctly is a constant challenge. Being able to recognize them at different scales and scenarios, sometimes cropped or badly lit, is not an easy task. Convolutional neural networks have become a widely applied technique since they are completely trainable and suitable to extract features. The growing number of convolutional neural networks applications constantly push their accuracy improvements. Initially, those improvements involved the use of longer data sets, augmentation techniques, and complex algorithms. All these methods have a high computational cost. Nevertheless, feature extraction is known to be the heart of the problem. For that reason, some approaches combine different technologies to extract better features to improve the accuracy without the need of more powerful hardware resources. Now, as an example, we have three studies that use the wavelets or the multi-resolution analysis. We need the convolutional neural networks and outside of it as an input. The first three examples, we can see that they use it for detect scenes, textures, compress images, detect and classify handwriting. Some of these use lifting scheme, which is a second generation wavelet transform, and some of them use adaptive forms of it. The second one uses a scalogram produced by the wavelet transform and then feed into the network to get the results they are looking for. So it's not part of the network, but it's like a new data set or a transformed one. Now, our hypothesis is that the convolutional neural networks, specifically the pooling layers, based on multi-resolution analysis, which in this case is wavelet transforms, may produce a better results, a better feature map. At the same time, they are reducing the dimensions by 2, like any other pooling process of 2 by 2 window. And in this case, we expect not to lose details, or at least not to lose the important ones or relevant ones that can achieve an enhancement in the accuracy of the network. Now, the four most commonly used pooling methods are the max pooling, average pooling, mixed pooling, and stochastic pooling. The max pooling takes the region, in this case, as I mentioned, a 2 by 2 region, and only selects the highest value of the region. And this way it performs a dimensional reduction. In this case, reduce the initial image, the initial matrix, by half. Now, the average pooling takes the 4 values of the region, in this case 4 values, and take the mean of those values to produce the resulting output for that image reduction. The mixed pooling takes these two, the max pooling and the average pooling, at a random base with 50-50 probabilities, and then produces the output as a result. The stochastic pooling is a little bit more complex. It uses just 2 steps. Takes the region, calculates the probabilities for each value. In other words, it takes the sum of all the values, and that's the 100% probabilities, and it takes a single value and divide it by the sum of the rest, and takes a small part of it, the probability. In this case, the 7 has a probability of 0.35. And in this base, it runs an algorithm that takes probabilities with these values and selects more likely the higher values than the lower, but it has the lower values has a chance, an opportunity to get picked up. In this case, 7, 5, 8, and 7 were selected, which are two of the highest values, or three indeed, no, two of the higher values, one the second higher value, and the third second higher value also. So it means that it's a tendency to the higher value, but not always is like the max pooling. Now, the wavelet transform, in this case, the lifting scheme works in this way. It first takes the signal, split it into even and odd values. Then it takes the difference, since p is -1, is just a subtraction, and all those differences form the details. It goes through a stage of normalization, and the other part of the lifting scheme takes all those differences and added up to the even samples, and this way takes like a mean or an average. And then it normalizes, and this way it produces the approximations. Now, for an image, a 2D signal, we have the same blocks, but we have to repeat it another 2 times. The first one split the signal in one sense, in the sense, vertical sense. It is split it by half, and then reduces the dimensions by half. And the other two takes the rest, and in the horizontal sense, it reduces it again and extracts approximations and details, and in this case, the first one becomes the approximations, and the other three becomes the details, the horizontals, verticals, and diagonals. Now, the methodology for this case was based on 4 benchmarks datasets, which are the MINST, which is a dataset form of digits from 0 to 9, CIFAR10, which are small objects, color images, and SVHN, which are the numbers of houses outside of the street. This can be one or more digits number. And the last one is KDEF, which is made of faces showing different emotions at different angles, men, women, and different ages form these samples of the dataset. Now, these 4 datasets are get into a convolutional neural network. In this case, the means use a simple one. It's not very complex, but it's very useful for this experiment. We have two pooling layers, which are the ones that we care, because in these blocks is what we are going to replace and put the 10 pooling methods that we are going to try and to evaluate. The CIFAR and the SVHN datasets uses this neural network since the image is a little bit larger and it requires more convolutional layers to get the patterns. And in this case, we have 3 pooling layers where we are going to replace the 10 methods I mentioned earlier. The only differences between these two datasets is the number of filters. The first one uses 32 and the second 64 filters. And the same here in the next convolutional block. Now, the last dataset is the faces one, and this is a little bit even longer than before. It's 128 by 128. It's a color images, and this needs more layers to be reduced and more, well, also 3 pooling layers, but it's a little bit complex images, and those images need more patterns to be learned, so that's why it uses more convolutional layers. Now, the 10 methods are basically the 4 most used. These serve as a state-of-the-art to evaluate the whole experiment. I already explained these 4, so the only thing is that we have to use it to replace the pooling block of the previous convolutional networks and put it one at a time. It's a 2x2 window in all cases. And also we change the pooling layers with the lift, which is a simple one, just taking into account the approximation. In this case, we are only showing one block, but it's two blocks just like this to produce the approximations. And the full lifting takes all four coefficients concatenated and use the whole block to replace the pooling method of each convolutional layers. Finally, the last four methods are hybrid ones, mixed ones. We take the lifting scheme for 2 dimensions for only approximations coefficients, but also in parallel we place this one of these conventional pooling methods one at a time. So it's lifting plus max, lifting plus average, lifting plus mix, and final lifting plus stochastic methods. And this way we form the 10 methods to evaluate. Now, after evaluating all methods using the 4 data sets, we can see that the highest results are mainly in the lifting plus max pooling methods. This one is the proposed method. We may think that the full lifting would be the best since it uses the 4 coefficients of the wavelets, but it's not. It's pretty good values. Those are pretty good values, but they are not the highest. The lifting alone is also a good method, and the max pooling methods is also a higher one, but none of them is good enough as the lifting plus max. Now, lifting plus average is very close to the max. It's extremely close. In some cases are equal, but is slightly superior to the max pooling method. In the example of the HVHN, I believe, we have the average pooling alone getting a better result than our method, but it's just one decimal number, and it's the only exception. In general, lift and max pooling are the method with the best results. Now, to sum up all these contributions, let me tell you that the lifting scheme in this case was implemented as a layer to be easily applied to the convolutional neural network and to be trained at the same time as the network. So it's just like another part of it, more layers. And the hybrid pooling method here was not previously considered. We also tested the hybrid pooling with the 4 existing methods to be sure that we were using all the possibilities and to find the best solution. The approximations are the only coefficients used in our model, which save us time and computational complexity. Instead of using the 4 coefficients, using only one is also an advantage. And the results compared with the 4 existing methods are pretty good, so we can achieve the dataset benchmark accuracy using these formats as comparison. So our method is outperforming the other methods. As a conclusion, I can tell you that the hybrid pooling method is better or has overcome traditional pooling methods, as we already saw, produce better results even than the lift alone or the full lift with the four coefficients model. What else? We propose the model outperforms in all dataset cases except for the ASVHN, which even though it gets a pretty good result, pretty close to the highest one, the pooling method, however, still depends on the input dataset and the architecture of the convolutional network. This means that in this case prevents overfitting and gets help the method to achieve a better accuracy, but in other cases it may result as the opposite. It may prevent it from learning properly or to get a higher accuracy method. So we need to implement a better method that can enrich this performance of the max pooling, but independently of the convolutional neural network architecture and the datasets or the input. And this is the last conclusion. The hybrid approaches enrich the accuracy of existing methods. We can use this as a lifting scheme in a whole block, as I mentioned here, to allow better developments of multi-resolution analysis combined with the convolutional neural networks. Now, the future work for this study includes the use of other wavelets like Lovich's and Kofflet's families, which also may produce relevant results, or even better, we have to test them since they have more vanishing moments and may find more features or more high frequency features. Also, if we elaborate a dynamical method that combines the coefficients of the wavelet, we may repeat results or may reach results as the max pooling combined with the lifting. As long as we analyze the responsive frequency of the max pooling, we can have an exact idea of what's the behavior of this max pooling layer, and then try to reproduce it with the wavelet coefficients, and we don't have to mix methods. We can explore a single method with better characteristics. Thank you very much for your attention.